Question 11 is looking for the relationship between an AMU in grams and the value of Avogadro's constant in per mole. So if you have a look in your data booklet, 1 AMU is 1.661 times 10 to the minus 27 kilograms. So therefore, it's 1.6 times 10 to the minus 24 grams. Avogadro's constant is, let me just look it up, Na is 6.02 times 10 to the 23. Okay. So what we can see is that the minus 24, or the kind of 1 times 10 to the minus 24, is very similar to the 23. So the difference between them, first of all, let's start at D. The difference between them is 0. This one's really small, this one's really big, so no, they're not the same number. Their sum is 1. No, if you add 1 AMU to Avogadro's number, you're not going to change this number. This number is so small, it wouldn't make a difference. So, no. Their ratio is 1. So what that is saying is if you had 10 to the minus 24 divided by 10 to the 23, that equals 1. It doesn't. Okay. So B, their product is 1. Roughly, yes. If you have 10 to the minus 24 and then you multiply it by 10 to the 23, minus 24 plus 23 equals 10 to the minus 1, which equals 1. So B. And remember, it's not exactly 1. 10 to the minus 1 is 0.1, but it's kind of roughly. Yeah, it's the closest answer out of all of them. Number 12 is talking about an ideal gas. Why do we get an increase in pressure of the gas? Well, it's actually B. It's an increased force on the container walls. The fact that they collide with each other is not one of the things that for an ideal gas. They don't occupy a greater volume. And if the average number of molecules increases, you must be inputting more particles. So that is incorrect as well. Question 13. When you have a change of phase, when you're going from solid to gas, so as you're going from solid to liquid to gas, as you increase the temperature, the internal energy increases, and so does the potential energy of the intermolecular bonds of the substance. So they both increase as you go from solid up to gas. So it's C. Question 14 is about, mine's gone blank, specific heat capacity. Energy equals mc delta t, delta theta, whatever value quantity you're comfortable with. So we have two situations. We have situation 1 and situation 2. Situation 1, E equals mc delta t. Situation 2, same equation. So number 1, when 1800 joules is supplied to mass m of liquid in a container. I'm going to put container MC. So we've got a mass of a liquid in a container that has mass. The temperature of the liquid and the container changes by 10 Kelvin. Okay. So, all right. When the mass of the liquid is doubled to 2m, all right, 3,000 joules. So we have 2m plus mc. C is required to change the temperature of the liquid and container by 10. What is the specific heat capacity of the liquid in units? Okay. So I think what we have to do here is sort out these brackets. So I think what we've got is 1800 equals 10 mc plus 10 mcc. And then over here, we've got 3,000 equals 20 mc plus, I probably shouldn't have used mc, plus 10 mcc. Okay. Right. So we know that 1800 minus 10 mass of the container times C equals 10 mass of the liquid, mass of the container C, and we know that 3,000 minus 20 mass of the liquid times C equals 10 mass of the container C. So we could put these equal to each other. Let's see if this works. All right, so we could cross through that and cross through that. So if I go in red for the end of it, so we have 3,000 minus so if we take the 1800 over and then we take the 20 over, we end up with this. Okay. So we say, I'm running out of space. So we say 3,000 minus 1,800 is 1,200. We can cross out these zeros. So 1 mc equals 120. Yeah, this is going to work. So 120 equals, divided by m equals c. And the answer is B. Is that correct? Let me just check the mark scheme. Yes, it is. Okay, that's question 14. Okay, so reading through question 15, where they're going to catch you out is the units for temperature. So we've got an ideal gas. So we're going to be using the ideal gas equation, and you must have your temperature in Kelvin. So we've got an initial situation and then a second situation. So the initial temperature is 20 plus 273, so 293 Kelvin. The second temperature is 20 degrees higher, so it's 313 Kelvin. Now I'm going to do an approximation. I already in my head know that I don't know my 313 times table. So I'm going to do some sort of approximation, I'm hoping, when I come to work out the answer for this one. So we are best off writing down the equation first of all. Now it's saying we're going to change the volume of the gas. We're not going to change the number of moles in the gas. So what I'm going to do is I'm going to cross out the constants. That's just going to make life easy for me. I'll keep the equal sign there. I should really change it to a proportional sign, but I'll just keep it there just to keep it nice and clean. So let me plug in a few numbers. An ideal gas has a volume of 15, a temperature of 293, and a pressure of 100. Okay. The volume of the gas is reduced to 5. The temperature is raised. So this is my raised sign, and this is my reduced sign, to 313. What is the new pressure? So in another color, I'm just going to show what's going on here. The volume has reduced by hang on. Right, my dog's just helping with the calculation here. So we can see that the volume has reduced by 3. Okay. But the temperature is almost the same value. Okay. It's slightly higher. All right. There's a slight increase, but very little increase. A slight increase in temperature from 293 to 313. Not a big increase, but the volume has dropped by 3. Now, if we want PV equals NKT on the first situation to equal PV equals NKT on the second situation, this P here needs to be at least 3 times bigger, because if we're dividing by 3 here, we need to times by 3 here. Okay, so if it was still 293, the new pressure would be 3 times bigger, which would be 300. However, we need this number to be slightly higher than 300 so that we can get to an answer that's just a little bit bigger than 293. So I'm just going to look for a number that's slightly bigger than 300. I've got one, and I'm going to go for it. Okay.